So we would like to use implicit differentiation to find y prime for this equation here. Let's go ahead and do that in the same manner we did in the previous examples. This time I'm going to begin by multiplying both sides by y to the 6th. So I take the left-hand side equation and I multiply it by y to the 6th. And then I take the right-hand side of the equation and I multiply that times y to the 6th. On the left-hand side of the equation, it makes more sense to write square root of y to the 7th as y to the 7th to the 1/2 power, or y to the 7/2 power. Or my preference is y to the 3.5 power. Now I can go ahead and multiply by y to the 6th a little bit easier. The left-hand side is going to be 9x to the 5th plus y to the 9.5 power. The right-hand side is going to be 23y to the 6th. And it's at this point when I can take a derivative of both sides. So this was just rewriting the equation. Now I take a derivative of both sides. That ends up being 45x to the 4th plus 9.5 y to the 8.5 multiplied times y prime. 23 times 6 is 138. So the right-hand side becomes 138 y to the 5th multiplied times the derivative of the inside function, which is y prime. This one is a little bit easier to deal with and solve than a couple of the ones we did earlier. So let's go ahead and solve this for y prime. What we're going to end up doing is taking every term which has a y prime, removing it from the left-hand side by subtracting, and then it ends up on the right-hand side. So I'm going to subtract 9.5 y to the 8.5 times y prime from both sides. And I will get this equation. 45x to the 4th equals 138 y to the 5th, y prime, minus 9.5 y to the 8.5 power times y prime. Hopefully that makes sense. I just subtracted this highlighted term from both sides. Now we factor out the y prime on the right-hand side, and then we divide by the coefficient of y prime. In the end, we get y prime is equal to a fraction. That fraction has numerator 45x to the 4th, and it has denominator 138 y to the 5th minus 9.5 y to the 8.5 power. And that's how we can use implicit differentiation in hard cases to figure out a y prime at any point. I should say any point where this y prime exists. Obviously, when y was 0, we didn't want to have y equals 0 because multiplying 0 on both sides is not the same thing as dividing by 0. So we wouldn't want to divide by 0. Same thing here. If I had 0 in as my y, we'd be dividing by 0. So other than when y is 0, this is a good way to find the derivative in order to find y prime. I have graphed this equation here You can see kind of the graph of the equation. It's really odd looking, really weird looking at the beginning. It kind of zigzags, and then it turns out looking like a square root after that. But this weird zigzag at the beginning is kind of an interesting feature. But my point of bringing this up is that at any point on this weird shape, we can actually find the derivative using that y prime that we just found. And so if I said, well, let's make a point on this to 1.6, then it's possible that I can find a derivative at that point. I can find the instantaneous rate of change at that point. Again, we have really odd shaped figure here, but it's still able, we're still able to find a derivative, even though this is clearly not a function because we failed the vertical line test. So there you go. That's the idea of implicit differentiation. It's the idea that we can find a derivative or find the instantaneous rate of change, find the tangent line, even in these really odd, weird looking functions. Obviously, this idea of implicit differentiation came out of the chain rule, because if I assume y is an inside function, then I take the derivative just as I would a chain rule, which means I have to multiply times y prime when I do that. And that leads me to be able to solve for y prime. There are a lot of other tricks you can use, some algebraic manipulation tricks, but the overall idea has been explained in this section. And that concludes this section.